In this video, we do an introduction to NMR spectroscopy, which NMR here, as a reminder, stands for nuclear magnetic resonance. We are not referring here to things like nuclear energy, but instead nuclear is referring to the nucleus of the atom. In a nuclear magnetic resonance experiment, the overall goal for the applications we're going to be talking about will be to determine the complete chemical structure of an organic molecule. So when we are looking at an NMR spectrum, there are a variety of different types of NMR experiments that we can run. In the next week's videos, we are going to get into a variety of different types of NMR experiments and how to interpret those NMR data to come up with the complete chemical structures of molecules. Those will include 1D NMR experiments such as the proton NMR spectra that you likely interpreted when you took organic chemistry. We will also get into two-dimensional NMR spectra that allow us to determine such things as which atoms are connected to one another or which atoms are close in physical space to one another. Overall, all of these different types of experiments and applications of NMR come back down to this phenomenon of nuclear magnetic resonance. And so that's what we're going to focus on in this unit, is some of the nuts and bolts of how does NMR work? What is the phenomenon of nuclear magnetic resonance? How do we experimentally measure that? And what are some of the things that will impact the quality of NMR data that we are able to gain? Because that quality of NMR data is something that is very practically important when we think about our ability to use NMR as a bioanalytical tool for determining the structures of organic molecules. So getting into the nuts and bolts of nuclear magnetic resonance, that phenomenon that we are measuring here, what it is going to rely on is the quantum mechanical property of certain nuclei referred to as the spin. Much like a top is able to spin clockwise or counterclockwise, some nuclei have that ability to spin as well as one of their quantum mechanical properties. Nuclei that are able to be detected by NMR include hydrogen 1, that is the most abundant isotope of hydrogen, carbon-13, not the most abundant isotope of carbon, but something that composes about 1% of the carbon that is naturally occurring. Nitrogen-15, another not so abundant isotope of nitrogen, but still exists in the natural environment. And phosphorus-31. Those are a few of the nuclei that we can detect by NMR. Certainly not an exhaustive list, but those are the ones that are generally most relevant when we're thinking about types of biologically relevant experiments that we can run. So just to get a list on paper for you of the nuclei that are detectable by NMR, those nuclei detectable by NMR are going to include, most commonly, proton NMR, which is detecting the hydrogen 1 isotope. That's why I put that 1 in superscript there. Carbon-13, nitrogen-15, phosphorus-31, and there are others as well, but those are the ones that we're going to focus on most frequently. And in this unit, as we continue onward next week with a variety of different types of NMR experiments and using that to deduce complete chemical structures, carbon-13 and protons are going to be the two main types of NMR that we will focus on in both one-dimensional and two-dimensional modes, which don't worry if you're scratching your head and going, what's 2D NMR right now? We will get into all of that in the upcoming videos. So in order to determine the structures of organic molecules by assembling together the atoms based on these nuclei that we can detect, what is common for all of these nuclei is that they all exhibit the quantum mechanical property of spin, where the nuclei is spinning like a top. And we'll use as our example here the case of proton NMR. And in the case of hydrogen 1 has what we'd refer to as a spin quantum number of 1/2. That is a known value from physics that would have to be a value that would be given to you. It's not something that you would be expected to memorize, but it has a spin quantum number of 1/2. And what that means is that if you place hydrogen atoms into a magnetic field, there will be two spin states, a low energy spin state and a higher energy spin state, one of which is at the -1/2 and one of which is at +1/2 as these two spin states. So has a spin quantum number of 1/2, has two spin states when you place it into a magnetic field. So you could think of that as two different ways that the top can spin. If we're thinking about a child's toy, the top. So we have two spin states when we place it into a magnetic field. And those two spin states are separated by an energy difference that we will describe as delta E, where the delta refers to a difference, E is referring to energy. So this is going to be the energy difference, is what we refer to as delta E. And looking at this schematically, this spinning in these two different spin states that are separated by an energy difference delta E is going to occur exclusively when the hydrogens are in a magnetic field. This will be occurring in a predictable manner. And so we can plot this out here as a schematic that if we had a proton in no magnetic field, we could plot the energy right here as this bar that I'm drawing in blue. And I'll go ahead and fill in on our y-axis here, just an arrow going up to indicate that the energy is increasing as we move upward there. So if we have no magnetic field, we have our relative energy there in blue. And then once we apply a magnetic field, what's going to happen is that magnetic field will stimulate the two spin states. And so as a consequence of that, the protons will adopt two different spin states, which I'm using the yellow dotted line to connect to those two spin states. One of those will have a higher energy. That's the one I'm drawing in right now with my blue kind of dashed line box, and a lower energy down here. These would correspond to the spin states of -1/2, corresponding to that spin quantum number of 1/2, or +1/2. And the important information here is the difference in energy between those two spin states. So what we were measuring here and interested in, that's going to give us ultimately information about the structure of the molecule, is that delta E value, the difference in energy between the plus and minus spin states for that particular nucleus. And those two spin states arise exclusively when the nucleus is placed into a magnetic field. So this delta E is what we are going to be measuring in order to ultimately get information that will allow us to determine features of the structure of the molecule. Now keep in mind that this NMR signal, this delta E value, is very, very small. And its very small magnitude is going to create some challenges in terms of developing a full NMR spectrum for a compound and determining the chemical structure of the compound. And so, in order to determine the complete chemical structure of the compound, it is necessary that we make that delta E value, the energy difference between the two spin states, as large as possible. And in order to make that as large as possible, what we can do is look at what is going to influence the delta E value. Now keep in mind that that delta E value is going to be proportional to the difference in population between the two spin states, the difference in the number of nuclei that are in this higher energy spin state versus the lower energy spin state here in the magnetic field, these two spin states. We can look at that population difference And that's going to be proportional to the difference in energy between the two. So let's see what we can do to manipulate that. So I'm going to put down population difference between those two spin states that we see in that magnetic field is going to be proportional to, and I use that alpha to indicate proportionality. It's proportional to the delta E value, where delta E, remember, is that difference in energy between the two spin states. So the bigger the difference in population between these two spin states, the larger the delta E value there. So how can we make the delta E value larger? Well, the delta E value and that population difference between spin states is going to be proportional to the following equation. So the following equation is gamma HB divided by 2 pi. Now, what do all of these variables represent within this equation? Because we need to know what the values are here in order to determine what we can manipulate to increase this delta E value to ultimately improve our ability to detect the NMR spectra of a compound. So our gamma value here refers to the gyromagnetic ratio. And that is dependent upon the exact nature of the nucleus that we are detecting. So that is not something that is variable. That is specific to a particular proton or a carbon-13 or whatever nucleus we are detecting. That is not something that we can manipulate. Our H value here refers to Planck's constant. That term constant in there is going to suggest to us that we can't play with that value. So that one is a no-go as well when we think about how we can improve the energy difference between our spin states or change the population difference between the two spin states in order to improve our NMR signal. So Planck's constant, can't manipulate that. Our B value refers to the magnetic field strength. This is a value that we can manipulate. More on that in just a sec. And then our 2 pi value, pi, of course, is a constant, 3.14. So we can't manipulate that. So what we're left with here as the only value that we can manipulate to ultimately impact and change that delta E value out of this entire equation is our B value there, our magnetic field strength. Magnetic field strength is measured in units of hertz or megahertz. Megahertz being a million hertz. And what is typical in NMR today is that generally instruments range from 100 megahertz to 1.5 gigahertz or even more in some cases. But 1.5 gigahertz is generally just about the top of the line. And so as we increase the magnetic field strength, we are going to improve the signal to noise ratio in our NMR experiment. So a higher field instrument is one way to create improvements, increases in the delta E value and increase the population difference between the two spin states to ultimately improve the signal to noise ratio, the S/N ratio of your NMR experiment. And so if you were given the choice and working with a molecule that you had very limited quantities of, such as a protein that you'd painstakingly isolated just a few milligrams of, or a small molecule that you had been able to synthesize just a few milligrams of, it can be very useful to utilize the highest magnetic field strength NMR instrument possible. In the chemistry department at UNF, as an example, we have a 500 megahertz NMR instrument. That's a nice middle of the road, middle of the line type instrument. If you instead were collecting data with a lower end instrument, the data quality would be considerably lower. If you worked with a higher end instrument, the data quality would be considerably higher. The trade-off here, because there's always trade-offs in life, or otherwise everyone would use the super high magnetic field instruments, is that the more magnetic field strength, the more expensive the equipment becomes, and also oftentimes the more expensive the maintenance is of that particular instrument, and as a result, the user fees for using the instrument is often much higher as well. So those are some things to keep in mind, that it's important to use an NMR instrument that has the magnetic field strength necessary to detect your molecule and give a good signal to noise ratio. The smaller the molar quantity of material you have, the higher the magnetic field strength you will need to be able to detect that compound. So how do we go about detecting that difference in population between the two spin states? In other words, how do we actually detect the NMR signal? How do we detect that population difference in spin states, which remember is proportional to the difference in energy between those spin states? Well, in most cases, the common NMR system is what's referred to as a pulsed Foia transform NMR system. So it's a pulsed FT, which is for Foia transform system. And the way that this works is that the sample within an NMR tube, a skinny long tube that goes into the NMR spectrometer and has your compound of interest, which I'll put in gray here, within a deuterated solvent, a solvent that rather than having a standard common isotope of hydrogen, instead has a hydrogen 1 replaced with deuterium. So your compound is in deuterated solvent. Deuterated solvent meaning there's only minimal hydrogen 1 in that solvent, and that's important because otherwise you would see a gigantic signal for the solvent, since the NMR instrument will detect those hydrogen 1 atoms. By using deuterium instead, hydrogen 2 in other words, that solvent becomes invisible. And so deuterated solvent with your compound solubilized in there, and that compound that you have solubilized has your hydrogen 1 present, and so it's detected in that pulsed Foia transform system. So this NMR tube is placed into the magnet, and what happens is that the sample that you have placed in this NMR tube is placed into the magnetic field, and there is a strong pulse of radio frequency. By strong pulse, we mean that the RF, the radio frequency, is not constantly bombarding the sample, but it's pulsing. It is on and then completely off, on and completely off in a predictable, timed out manner. So there's a strong pulse of radio frequency, and what that is going to do is that excites all of the active nuclei. When we say active nuclei, we mean, in this case, the hydrogen nuclei, hydrogen 1, the specific nuclei that are able to change spin states. So all of those active nuclei are excited simultaneously. And then what happens is that, since it is a pulse, it ultimately stops. And the nuclei lose energy because they are no longer present in that RF field. And then this process of exciting the nuclei to go up to the higher spin state, stopping the pulse so they go back to the lower spin state with the nuclei losing energy, is repeated. So steps 1 and 2 are repeated. We refer to this as the number of scans. That's the number of iterations of this pulse going on, so that the nuclei gain energy and then lose energy systematically through the gain and loss of energy corresponding to the two spin states. And we repeat that for multiple scans because ultimately those multiple scans are going to be Fourier transformed and averaged to yield the NMR spectrum. So ultimately, after this is repeated, the resulting data are going to be Fourier transformed to yield the NMR spectrum that we recognize. And we will show lots of examples of different NMR spectra and types of NMR spectra in the upcoming week and the upcoming videos. For now, when we think about the practical aspects of NMR, we mentioned previously that one way to improve the quality of data, improve the signal-to-noise ratio, is to use a higher magnetic field instrument. Another way to improve the signal-to-noise ratio is to run more scans. So you might think that the number of scans here, the number of pulses of radio frequency that are used, would allow us to linearly increase the signal-to-noise ratio, but that is not correct. Instead, the number of scans relates to the increase in signal-to-noise ratio as the square root. So while it is true that the number of scans increases and improves the signal-to-noise ratio, what the signal-to-noise ratio improvement is actually proportional to, and we'll use this alpha value to indicate proportionality again, is it's proportional to the square root of the number of scans. And so if you double the number of scans, you are not going to double the signal-to-noise ratio. Instead, how you can calculate that, if you're thinking about the improvement in signal-to-noise ratio and thinking about how many scans should you run if the data are like kind of halfway to where they need to be, they're a bit noisy, the signal-to-noise ratio is not great, the data don't look terrific, but you want to make the signals nice and clean and clear. If you want to improve the signal-to-noise ratio by a factor of 2, then you need to think about what your change in number of scans is that would equal 2. And so your number of scans, how many scans you would have to change by, the factor that you would have to change by is a factor of 4 because the square root of 4 equals 2. And so if instead you just increased the number of scans by a factor of 2, you would take the square root of 2, because that's the change in the number of scans. You take the square root of 2, you get 1.4, and that would be your improvement in signal-to-noise ratio. So, in other words, doubling the number of scans, that's what we show here, is that the change in number of scans is that we've doubled it, is only going to give you a 1.4x improvement in the signal-to-noise ratio. And in the other hand, in order to improve the signal-to-noise ratio by a factor of double, by a factor of 2, if you change the number of scans by a factor of 4, so you plugged in 4 here as the change in the number of scans, the square root of 4 is equal to 2, so that would give you a 2 times improvement in your signal-to-noise ratio. So that's another way to go about optimizing an NMR experiment, is to increase the number of scans. So that leaves us with sort of the bottom line here in practical terms of thinking about improving the signal-to-noise ratio, which is a common thing that one needs to do, particularly when looking at biomolecules where we have very limited quantities of substance that we're looking at, is increase the number of scans. And if you need to dramatically increase the signal-to-noise ratio, you're going to need to even more dramatically increase the number of scans, because the signal-to-noise ratio increases the square root of the change in scans that you've done. The other way to improve your signal-to-noise ratio is to get an instrument that has a higher magnetic field, because that will accomplish it as well. And keep in mind here, when we think about the sensitivity of NMR and the sensitivity of this experiment, the signal-to-noise ratio you can ultimately obtain, is based not on the mass of material that goes into your NMR tube, but instead the number of molecules that go into the NMR tube, or the number of moles, in other words. And so as a result, the molecular weight of your compound determines how much compound you need in order to be able to collect a suitable NMR spectrum. So keep in mind that the sensitivity, our ability to detect, and our signal-noise ratio is ultimately based on the total number of molecules that you are subjecting to this nuclear magnetic resonance phenomenon. And we could think of the number of molecules as being, proportional to the number of moles, not on the mass of the compound. So in other words, if you have a molecular weight compound that has a molecular weight of 2,000 versus molecular weight of 200, what that's going to mean is if you had, say, 100 milligrams of each of those compounds, for the compound that you had a molecular weight of 2,000 for, there would be far fewer moles than if the compound only had a molecular weight of 2,000. It would have far more moles contained in that 100 milligrams, because if you did the calculation for how many moles you have of 100 milligrams of substance with a molecular weight of 2,000, you're going to find that number of moles to be much lower than if you had 100 milligrams of a substance with a molecular weight of 200. So if you do your mole calculations there, you're going to come up with far fewer moles for 100 milligrams of the molecular weight 2,000 substance than the molecular weight 200 substance. And as a consequence of that lower number of moles, you're going to have a lower sensitivity in the NMR. And so that means that you would need such things as more scans and a higher magnetic field to detect a compound with a molecular weight of 2,000 versus 200. And so that's one reason why the evaluation of proteins is extremely challenging in some cases by NMR, is because those are very high molecular weight compounds. So that makes protein NMR more complicated, in addition to the fact that there are such a large number of atoms in a protein NMR spectrum, making this spectrum very complex as well. So what we will do in the next several videos is dive into the application of NMR data in both 1D and 2D modes to determine the structures of unknowns, a very powerful technique for evaluating compounds of biological relevance.